Good morning, students. In the last class, we have discussed about the construction and working of P-channel JFET. Today, I'll be starting with the working of P-channel JFET. So, as you can see in this figure, the name itself indicates that it's a P-channel JFET. So, P-channel JFET means the intermediate channel here, as you can see here, this is P-channel, and on either sides, it's of N channel. Okay, so intermediate channel is P, which is sandwiched between two N layers. So it is a p-channel JFET. Okay. So to this p-channel JFET, the terminals remain the same as that of the n-channel JFET, that is source, gate, and drain terminals. Source, gate, and drain terminals. Whereas the current direction is reversed. Let us see how the current direction is reversed here. We are applying the voltage VGG, positive negative voltage between gate to source VGG, and negative to positive voltage VDD or VDS between drain to source terminals. So when we apply this voltage, that is a negative of the VDS or negative of VDD, right? It repels, it attracts the minority carriers, minority carriers. That is, it attacks the holes, right? It attacks the holes of the P type here. So the current that is the current in the P channel JFET is due to the holes that are present in the P channel, and it repels the negative charges. So as it repels the negative charges, the width of the depletion region decreases. So here, due to the negative plate of the VDD, negative of the VDD is repelling the negative charges of the N channel. So the width of the depletion region decreases here. So that is how the current ID flows, that is due to the holes in the P channel JFET. So this is the working of the P channel JFET. P channel JFET is constructed in exactly the same manner as N channel device, but with reversal of P and N type materials. That is, in the N channel JFET, the channel is N, whereas in P channel JFET, the channel is P, and on either sides it is N layer. Current directions are also reversed. In the N channel JFET, the current is moving from top to bottom, whereas in the P channel JFET, the current is moving from bottom to top. The current directions are reversed. For P-channel device, the channel width will decrease by increasing positive voltage from gate to source, and for negative voltages of VDS. That's what I told. So as we increase the VDS or VDD, so it is repelling the negative charges. So the width of the depletion region decreases. Next, we will see the FET small signal model. Small signal AC model is developed with the following facts. That is, impedance between gate and source terminal is very high for the FET. So as the impedance between gate and source terminal is very high for the FET, the current is very less, and hence it is treated as an open circuit between gate and source terminals. It is treated as open circuit between gate and source terminals. Then the drain current is controlled by the gate to source voltage. This I have explained at the beginning. The gate to source voltage controls the output current or the drain current, as it is a voltage control device. If it is a voltage control device, that is, we say that ID is proportional to VGS. ID is proportional to VGS, or if we equate this, we get ID equal to GM VGS, where GM is called as the transconductance of FET. GM is called as the transconductance of FET. So GM is ID by VGS, that is current divided by voltage. So it is the conductance or the transconductance of the FET. As per the equation 1 here, so this is our equation 1, ID is equal to GM VGS. As per this equation, as I told, it is a voltage controlled current source or a voltage controlled device. ID equal to GM VGS is between drain and source terminals. So between drain and source terminals, it is modeled as the current ID that is given by GM into VGS. And in saturation region, the current ID is proportional to the drain to source voltage. We have three regions, that is active region, cutoff region, and saturation region. In the saturation region for the FET, the current ID is proportional to VDS, or ID is equal to 1 upon RD into VDS. So if we take for RD here, RD will be equal to V by I, or RD will be equal to V divided by ID. So it is a resistance. So what is this resistance RD, students? RD is the output impedance of the FET. I hope everyone are following here. Yes. So RD is given by 1 upon YOS, where YOS is the admittance. It is a reciprocal of the resistance. So YOS is the output admittance, which is the reciprocal of the resistance. That means what here? FET can be modeled as a resistor RD between drain and source terminals. So between drain and source terminals, FET is modeled as the resistor RD or the drain resistance RD. So with all these data, we will be drawing the FET small signal model, AC model for the FET. So which applies for both N channel and P channel FETs. Whatever is the model that we are drawing here, the small signal AC model of FET, it applies for both N channel and P channel FETs. So in general, this is the FET small signal model for both P channel and N channel FETs. So as I told, between gate to source terminals, high input impedance, and it is modeled as the open circuit. Okay, so it is VGS, whatever gate to source voltage is applied here, that is the same voltage. Then the drain current is modeled as ID is equal to GM VGS, so it's a drain current ID flowing between drain to source. Then the output resistance RD, the drain resistance RD, as we can see here, is connected between drain to source, that is RD is equal to 1 upon YOS. Okay, so here it is written ID is equal to 1 upon RD into VDS, or RD is equal to 1 upon YOS. Fine, students. Next, we will see the JFET common source amplifier using fixed bias configuration. This is JFET, junction field effect transistor, or the field effect transistor. Okay, here it is JFET common source amplifier using fixed bias configuration. So here we have source, gate, and drain terminals. Okay, then here we are biasing, connecting the voltage VGG through resistance RG. So it is a fixed bias configuration. So fixed bias configuration means constant voltage VGG is applied between source to gate terminals. Constant voltage VGG is applied between source to gate terminals, and hence it is called as fixed bias configuration. And on the drain terminal, the resistance RD is connected to VDD. Then we have coupling capacitance C1 at input and coupling capacitance C2 at the output. The input voltage is VI, the input impedance is ZI, right? And output voltage is V0 and output impedance is Z0. So this is a circuit of the JFET common source amplifier using fixed bias configuration. So this JFET common source amplifier is similar to BJT common emitter amplifier, or it is similar to the common emitter amplifier of the transistor circuit. So here we are seeing the circuit of common source amplifier using fixed bias configuration. Again, due to high input impedance of JFET, the DC current through RG is assumed to be 0. So the input impedance of the FET is very high, and hence the DC current flowing through the FET here, DC current flowing through the RG here, right, it is assumed to be 0 because of the high input impedance of the JFET or the FET. Fine, friends. Then constant bias voltage VG is applied between gate and source, and hence the name to it is called as the fixed bias configuration. The input coupling capacitor C1. So this is input coupling capacitor C1. So we know the function of, or the importance of the capacitor. So this capacitor always blocks DC, because for DC the frequency is 0 and infinite reactance XC, and hence it blocks DC and passes the AC signal. Okay, so this is C1 is isolating the input AC input voltage VI from the DC voltage VGG, because it blocks the DC and passes only the AC signal. Similarly, the output capacitor C2, the output coupling capacitor C2, it is isolating the DC voltage VDD from the AC output voltage V0. Again, it is nothing but the same function, as it is a capacitor only, it blocks the DC and passes only the AC signal. Next, we will be going through the AC equivalent circuit. AC equivalent circuit is obtained by, we know how to obtain the AC equivalent circuit, we have studied in module 2. It is AC equivalent circuit is obtained by short circuiting the capacitors C1 and C2 and making the DC voltages 0. Okay, so whatever are the DC voltages here, VDD and VGG, they are made zero, so it is a short circuit here. Then capacitors C1 and C2 are short circuit for the AC signal. It is the AC modeling. So here the circuit will be modified to in this form. This is RG, it will be shorted here. It is VGG is made zero, and here there is a short circuit. Okay, then here RD is connected to zero. That is VDD is made zero. So RD is connected to zero means there is a resistance RD connected between drain to ground. VDD is zero means it is as good as a ground. So RD resistance is connected between drain to ground. That's what it is shown here. So RG is connected between gate to ground. RG is connected between gate to ground here, gate to ground. Then here we have drain resistance RD connected between drain to ground. And input impedance Zi, Z0, input voltage Vi and V0 are shown. Now let us replace JFET by its small signal AC equivalent circuit. AC equivalent circuit, as I discussed at the beginning. So this is the AC equivalent circuit, small signal model for the FET. We have VGS, GM VGS, and resistance RD at the output. Okay, the same will be used in drawing the AC equivalent circuit for the JFET circuit, which we are discussing now. So this is VGS here. We have GM VGS and small RD. Then the input side we have resistance RG, this is resistance RG, and output side we are having the resistance RD. So the same we can represent here. We can draw here the input resistance RG, right, and the output side we have the resistance capital RD. So we have input Vi, then Zi, input impedance, output V0 voltage, and output impedance Z0. This is the small signal AC equivalent circuit of the JFET. Let's find the input impedance here. We see in this circuit, we have the in open circuit between source to gate. We have open circuit between source to gate. Hence, the input impedance, if you look from the input terminals Vi, right, the input impedance is nothing but it is RG. Yes or no, students? The input impedance Zi is nothing but the resistance RG. So that is the input impedance is nothing but the resistance RG, because it's an open circuit between source to gate. If there was some resistance here, then there would be a combination of this RG and this resistance, which would be present between source and gate. But as the source to gate is open circuit, and hence the input impedance simply the resistance RG. So about the output impedance and other performance parameters we'll see in the next class. In today's class, we have discussed about the P-channel JFET, its construction and working, then the FET small signal model, how to develop the small signal model of the FET using various equations. This is the FET small signal model. Then moving on to the JFET common source amplifier using fixed bias configuration. It's called as fixed bias configuration because the constant voltage VGG is applied between source to gate, and hence it is called as fixed bias configuration. Then later we discussed about the small signal AC equivalent circuit, how to draw the AC equivalent circuit, and how to develop the small signal AC equivalent circuit of the JFET. Then we have seen the input impedance equation for the JFET circuit. Okay, JFET circuit. The input impedance Zi is given by the resistance RG. The next class we will be discussing about the other performance parameters of the JFET circuit. Okay. Hope everyone have understood here. If there are any questions on today's discussion, on today's class, please send your questions to me. I'll answer to your questions. Thank you.